Our next speaker will be Professor Zhang. So Che is an assistant professor in computer science at ETH Zurich. His current research focuses on building data systems to support machine learning and help facilitate other sciences. He finished his PhD round-tripping between the University of Wisconsin-Madison and Stanford University. He contributed to the research efforts that won the Sigmoid Best Paper Award and Sigmoid Research Highlight Award. So his talk title is Towards Understanding End-to-End Learning in the Context of Data. So let's welcome Che to give his talk.
Thank you very much for the introduction. Hi everyone, thanks for coming to my talk. So today I'm very excited to share with you some of the progress I'm making. You try to understand essentially end-to-end like data pipelines and machine learning. So I myself is a database guy, right? So the first time I go to CVPR, I'm very excited about this. So today I'm going to talk about our efforts here, but also some of the somehow unexpected connection to the result we have to machine learning robustness. Unexpected in the sense that when we were first trying to do it, we have no idea that it's somehow connected to machine learning robustness. Okay, great. So I think everyone here have witnessed the rapid progress that people are making in machine learning and machine learning systems over the years. Compared with, for example, 10 years ago, training a single machine learning model become much faster. And on the other hand, the training itself also become more automatic and more systematic. If you think about why that could happen, right? So on one hand, almost all the major cloud service providers are actually pushing towards these two directions. And on the other hand, there's a whole bunch of research projects try to develop the next generation of machine learning platforms. So given all of these efforts, so I think it's very kind of fair to say that today, getting some machine learning models, given a training set, has never been easier. But on the other hand, so I would argue that our ability to really understand the training process has not been improving with the same pace. And today, however, many of the machine learning problems to the core is more like a data problem. So the understanding has never been more important. So there are multiple aspects that you want to understand. And there are multiple reasons that you want to understand this. On one hand, it is the accuracy, right? How can I get a machine learning model with best accuracy? If you look at where we are today, right? So this is actually one benchmark that we have been keep running over the last 5 years. So today, if you just give the raw feature from Kaggle to the top 4 machine learning platforms, right? So most of them will give you some machine learning model rank to the bottom 50%, right? So essentially, it is the data that we to improve the machine learning accuracy, and also we need to integrate knowledge to improve the machine learning accuracy. But however, before we can do any integration, we can need to understand them. That's why understand the training process with respect to data is becoming more and more important. And on the other hand, it's about robustness, right? Because we want to understand the sensitivity of machine learning training or machine learning inference with respect to data, right? So that's why understanding of the machine learning training process, in my opinion, has never been more important. So in this talk, I'm going to talk about 2 problems that we want to understand from really abstract way, and then I will talk about its connection to robustness. So on one hand, I have a training set, and there could be a lot of data problems, right? So I could have missing value, or I could have either some perturbation introduced by adversarial parties, or I have some noise introduced by the nature, right? So I pipe this into a machine learning training process, which gave me some machine learning model. And then we can start to evaluate it to try to calculate some utility, maybe the validation accuracy, the fairness, or robustness, so on and so forth. So I care about 2 questions. The first question, because I have all those data problems, which one should I fix if I want to increase my utility? And also, what is the most influential data problems that I'm facing to my accuracy, fairness, or utility of the final model artifact? So, and the second question is, because I have many training examples, which one is to blame, or which one is most important for my final utility? So this is the 2 questions that I care about. So as you can see, if we have a principled understanding of these 2 questions, it can really unleash a whole bunch of problems and have profound impact on the development and the operational aspect of machine learning, right? So it can really help us to understand the robustness of the machine learning training process with respect to data problems or different data examples, and also can kind of enable a whole bunch of applications like data cleaning, so on and so forth. So it shouldn't come as a surprise that people have been looking at this for a while, right? In the database community, people have been working on how to do data cleaning for machine learning, right? And also in the machine learning community, people have been looking at inference functions and also Shapley value, right? To really understand these two questions. So what's the problem for us, right? So the problem for us is the following. That is, when people are trying to understand these two questions, this seems to be everyone's mentality model. You have the data, you have the training, you have the model artifact, you have utility. However, if you look at real world machine learning applications that you get from data scientists, so somehow they look like this more often. That is, you have data, you have a feature extraction pipeline, which is a feature transformation over your input training side. And then you train a machine learning model over that, get your model, then you can measure your utility. So the fundamental challenge is really these components, the data transformation components, because they are discrete, you cannot take derivative over them. It can really make the problem much, much harder. And that is actually the goal of our scientific endeavor. So essentially, given this, we call end-to-end machine learning pipeline, feature extractor, the training process, we try to understand these two questions. What is the most influential data problem? And also, which training example is most important? So to understand these two questions, we are curious about two fundamental quantities. For the first question, we are actually curious about the entropy and expected prediction over all the noise in your training example. And also for the second question, we are really curious about expected improvement of the Shapley value of each training example. So I'm going to talk about more in the abstract way about how to do these two questions, and then I will connect them to robustness to see what the application we can enable if you can assume we can compute these two things. So if you look at these two quantities, it shouldn't come as a surprise that they are very hard to compute, right? There's entropy, the Shapley value, right? In generic case, and they're Shapley complete. So our result center around a very simple trick. That is, if you take this end-to-end machine learning pipelines, somehow you can construct a pipe-C pipelines by introducing some of the heuristics and simplification of the given pipeline. For example, you can approximate the noisy model, right? Using something called cost table, which is something I'm going to talk about later. You can actually approximate the feature extraction pipeline into something simpler, right? For example, here we are doing a positive relational algebra queries, right? You can approximate your machine learning training process into, for example, a simpler model like k-nearest neighbor classifier, and then you measure the utility. So our goal is really try to revisit that two questions for this pipe-C pipeline and use that as a proxy for the real pipeline. So as I'm going to show in this talk, the first takeaway is actually for a dominating number of realistic pipelines. If you look at your proxy pipelines, we can actually compute exactly in p time the entropy, the expected prediction, and Shapley value. So that's actually something really surprised us in the beginning. The second takeaway is as long as you can compute these fundamental quantities, it really provides a principled framework for many applications. So most relevant to robustness is it actually gives you a kind of principled way to certify, to provide certified robustness for backward adversarial attacks. It can also kind of enable things like data debugging for robustness, how to do data cleaning for machine learning, so on and so forth. So the way is that pipelines, like using the proxy pipeline as a proxy, really works well. So empirically, it's also work well in cases. Okay, so in this talk, I'm going to talk about two. Give me 15 minutes, then we talk about theory, right? So talk about what we know how to do and what we do not know how to do. And then I will switch gear into applications. I will talk about 3 different applications. The first application is how to do essentially certified robustness for backdoor attacks. And second, how to do data debugging, right? To really pick out in the training set some, for example, potentially being attacked images, right? And the third one is how to do data cleaning for machine learning. Okay, so now let's talk about theory. So we have 2 theoretical questions. For the first one, this is the setting. So you have your training set, and then you have some uncertainty or noise in your training set. For example, for some of the cell, so I don't know the right answer of this cell. That I know it can only take, for example, 2 alternative values or multiple alternative values. You have noise. And then you want to train a machine learning model over this noisy data set. You have the utility, you try to understand what is the impact of different data noises to the final machine learning accuracy, because not all the noise actually matters. So before we kind of try to define what do we mean by this question, let's try to look at what does it even mean by training a machine learning model over uncertainty, right? Because I mean, at least I don't know what that even means, right? So you have an input data set with a whole bunch of uncertainty, you train a machine learning model. I mean, what do we mean by that? So I'm a database guy. Whenever I'm not sure about how to define something, I always go back to database and try to understand what the field are doing over the last half century, right? So essentially, if you think about your database systems, so there's actually a long line of study how to do information processing over uncertainty. So essentially, in a database system, you have notion of right to really tell people, there's actually certain amount of noise in the cell, and then try to have a principled way to answer SQL queries over unknowns, right? So that probably brings us to all of our nightmares when we are doing our undergraduate study. That is actually the norm, right? So essentially, in database, whenever you have a training set or like a data set, whatever, if you do not know the value of certain cell, right? So you can put a special state called null there, and then you can actually answer SQL query over this relation, right? For example, if you have relation look like this, right? You say, this is my SQL query, right? Your answer will be look like this. Why? Because I cannot compare null to 30. That's going to give me unknown, so I'm not going to return Kevin in the result. So how can we do machine learning over this? That's actually the question that we are curious about. So before we define that for machine learning, let's try to understand really the formal semantics of null in database. If you open whatever like database theory book, you can see the semantic. On one hand, you have relation with uncertainty. Whenever I'm answering some query over this uncertain information, what the database is actually trying to do underneath the cover is try to expand that into a whole bunch of possible world without uncertainty. Right? Each possible world corresponds to one possible valuation of that unknown data cell. And then you do the SQL query over each of them, you get the result, you calculate the intersection, and return what they call the sure answer or certain answer of this thing. So if you take this view, as you can see, there probably nothing stop us from doing this for machine learning, right? Because we can just apply this to machine learning in the following way. Assuming you have a relation with uncertainty, for example, for this cell, we have no idea what the value would be. I have a certain amount of noise. For example, you have a uniform kind of prior over 3 values, 1 to 30, for example. You can actually expand that into a whole bunch of possible world, each one of them corresponding to one possible value for that cell. And then if you say, okay, I want to train a machine learning model over this uncertain information, and then I want to make some prediction, what you can do is you can take every single possible world, do that, train a machine learning model, predict on some tuples, and then you aggregate the result. If the result is all, for example, you have a binary classification problem and they all predict yes, right? So your answer will be yes, that's a sure answer, they agree. If everyone say no, you return no. If someone say yes, someone say no, right? So you have no, right? You can also aggregate them in a softer way. You can calculate the expectation, right? Or you can calculate the entropy, right? So as you can see, this can also connect to robustness a little bit, right? So essentially you are saying that, okay, so I have a noise in my input example, right? How many possible worlds will that affect the prediction, right? So that's actually what the entropy and expectation try to measure. So essentially, given an input relation or input training set with a known noise model, right? So we can actually define a probability distribution over many of these possible worlds. And then given a test example, you can define the expectation. So you can calculate the expected prediction on X as you train a single machine learning model for each possible world, you do some prediction, then you aggregate the result. We can also define essentially the entropy here, right? Like over all the possible world. So the intuition about why this is useful, right? Essentially, if you think about data cleaning, right? So when the entropy goes to 0, right, it means that the training process is 100% robust to the input noise, right? It doesn't matter, right, how you change your input value, right? My prediction will not change, right? For robustness of data cleaning, this gives you the measure of how robust and how sensitive the training process is to the given noise model in your input, right? So that's why it could be interesting. Okay, so what's the challenge here, right? So as we can see, this thing could be really computational expensive, right? If you have a table with n rows and d columns, right? And even if for every single cell you have two possible like values, right? So you need to enumerate 2 to the n times d number of possible rows. So here's what we know. For general classifiers, we don't know how to do better, right? So it's sharply complete, right? So and probably can only CMC. However, if you look at our proxy pipeline, for example, k-nearest neighbor classifier, right? So we are able to have a linear time algorithm to enumerate all these exponential many possible rows. So that actually surprised us in the beginning. So I'm not going to the technical detail. You have to trust me or check out this paper. It also applies to end-to-end machine learning pipelines when your feature extraction pipeline only have map operators. Okay. So the second theoretical question before we go to the application is how to calculate the Shapley value over end-to-end machine learning pipelines. So here's a setting. So I have an input relation R, contain my training data, and then I pipe that through a feature extraction pipeline, and then I get my transformed training set. I train a model, and then measure the utility, right? So I want to understand essentially what is the importance of each training example to the final machine learning accuracy, because not all the input example actually matters. So here we actually define that, define the simulator measure as expected marginal improvement, right? For example, I have an input training set with, for example, 4 different tuples. And then I try to understand the importance of the right tuple. So what you can do is, okay, I calculate the utility of the whole data set, then remove the right tuple, and I see the potential improvement of the accuracy, right? So this can already tell you something about the importance of the right tuple, right? So, and then if you think about inference function, right? So this is actually what it is trying to do. But you can do a little bit more. For example, you can enumerate all the possible ways you can arrange the rest of the tuples, right? And for each possible world, you can calculate some improvement value, you can aggregate them, and then use to answer this question. So there are different ways you can aggregate them, but if you aggregate them in a certain way, that gives you something that people call Shapley value, right? Which is the concept in game theory, has a very useful theoretical accommodation, many good properties, and people have been shown really works really well for data debugging, right? But of course, when people like look at them, right? So they actually do not look at the feature extraction pipelines. So here's what we know, right? So the fundamental challenge here is again, right? So I need to enumerate exponential many possible rows, right? And also for each one of them, I need to run feature extraction, I need to run machine learning training, I get the model and measure. It can be ridiculously slow, right? So here's what we know on. So first one, again, for generic classifier, I have no idea how to do better. It shall be complete, probably into the MCMC. However, if you look at our proxy pipelines, where the feature extraction pipeline is like have different properties, but your machine learning model is a k-nearest neighbor classifier, you can actually do significantly better, depending on what feature extraction pipeline. So you have different time algorithms calculate exactly the Shapley value. So that's actually something that actually surprised us quite a lot in the beginning. Okay, so that's enough for theory, right? So essentially for the proxy pipelines, I try to convince you that if you want to calculate the entropy, want to calculate expectation, want to calculate Shapley value, if you allow me to use a proxy model, I can do that exactly in Kita. So now let's try to think about, okay, so assuming we can calculate them, how can we use them? What's the connection of the theoretical result to robustness? So this is actually one thing that one result we have together with Bohr, actually, right? So, and essentially here's the setting. So it's a standard backdoor attack setting, right? So we have a training set, and then someone put a very small pattern into your training set and flips the label, right? So if you train a machine learning model over this noisy data set, if you give me a binary test example, it's going to be fun, right? If you give me another adversarial test example with the same pattern, right, highly likely the model is going to give you the wrong prediction. So the question that we try to understand is, can we make our training process robust to this type of attacks, right? So how can our understanding of the end-to-end training process help us here? So the high-level idea is, let's try to inject noise to the training set and compute the expectation, right? So this is such a natural idea, right? So it's kind of inspired by runtime smoothing about how they do invasion attack, right? And also kind of like inspire how people are doing differential private training over the training side, right? So it's such a natural idea. However, if you do this, right, you are able to get, at least to our best knowledge, one of the first certifiable robustness kind of like guarantee for backdoor attacks. So here's actually how we think about this. Before we talk about specific backdoor attack, we actually look at a more generic question about the robustness of expectation. Okay, so it's kind of inspired by the seminal work of Ren and Smoothing, just such an inspirational paper. Here, what we are trying to do is try to slightly, right, generalize it. So here's our setting, right? So we have one expectation, right? So you will have z draw from some distribution, and you have one function fxz, right? So that give you a function gx. We try to understand what can we say when you have gx and gx plus delta, right? So the general theorem that you can have is that you can actually apply hypothesis testing or quantum hypothesis testing, depending on like your assumption on x, to give us certificates that are very similar to random smoothing, but more generic to more generic type of like distribution that you have. And once you have this, you can actually plug it in to different scenarios to make some claim on robustness. For example, for the defender gun backdoor attack application, right? So your x is actually your training set, right? And then your z is actually the Gaussian noise you injected to your input training set. And then this fxz is essentially I kind of do some perturbation z on my original training set x, and then I train a model over that, then I do my inference, right? So if you take this view, combined with the general theorem, you can actually give certificates against backdoor attacks, right? So as long as the attacker introduces perturbation delta smaller than certain norm, right? So then the inference result will not change by this much, right? So this is a certificate that you are able to give. If you have a generic training process like a deep neural networks, right? So the best you can do is you sample some training set, then train a model for each, then aggregate the result. So that's good enough. You can do MCMC. However, if you are talking about k-nearest neighbor classifier, you can actually get this certificate in p time exactly, right? You do not need to do sampling as random smoothing, right? Here you can actually compute the whole thing, right? Because that is something that we cannot know how to do if you have a k-nearest neighbor classifier. So there are more results. If you are curious about it, just check out this archive paper we have with Bo. So since you have this kind of generic view on this, right? It doesn't need to be classical, right? So you could actually use this to certify robustness of quantum systems. So here, for example, this x could be n qubits, right? So that's the input state of your quantum computation system. And then this fx can be your quantum circuits, right? And then when you calculate this expectation, that's your measurement, right? So that's actually the result of a quantum system. So if you take this view, you can actually plug it in and try to get the certificates for quantum computation systems. You can have a certificate look like as long as the attacker introduces the perturbation, but do not decrease the fidelity like lower than some constant, right? Then the result of your quantum computation system will not change by this much, right? So it's a lot of fun, right? So like one thing that's interesting is because there's the notion of kind of inherent type of kind of randomness in quantum computation, right? You actually do not need to inject noise to get the robustness here, right? You kind of get robustness code for free, right? For quantum systems. And you can do more, right? For example, there are people start to do those like neurosymbolic type of systems where they have a neural network followed by a joint inference component, right? Maybe a Markov logic network, maybe a conditional random field, so on and so forth. You can take this view to also kind of certify the robustness of those type of systems, right? Where your X could be the output of your neural networks, right? And then it's followed by some joint inference components, right? Maybe a probability SQL query, maybe Markov logic network for knowledge integration, right? If you combine this with the informal theorem that we have here, right, you can also get the certificates of the end-to-end pipeline. You have machine learning, have joint inference, right? How to certify robustness of the neurosymbolic type of system. That's also something that you could do here, right? So together with Bo, we actually have multiple like attempts, like here, one deal with Markov logic network, another with conditional random field. Feel free to check out these papers. So this is actually something that we didn't expect when we start our endeavor, right? We start from a pure database perspective. We really want to understand how to calculate entropy over noise, right? And then surprisingly, that brings us to robustness. And we had a lot of fun over the last couple of months, like to really come up with those results. So another thing that you can also use our results for is actually for data debugging, right? So assume you have a training set here, right? So some of the image have the wrong label, as you can see, right? So the question is, how can we find out those training examples with wrong labels, right? The head of idea, you can actually look at those data examples with small or negative Shapley value, right? So because the head of idea is if you calculate their marginal contribution, those kind of images with the wrong label contribute in expectation negatively to the final utility, right? So if you have a machine learning pipeline, if you allow me to use a proxy model as a proxy, right? So I can actually compute that in P, right? Kind of orders of magnitude faster than MCMC, right? So given like, for example, 100,000 image in the training set, calculating the Shapley value for every single one of them kind of less than like 1 second, right? So, and it actually works pretty well, right? So the x-axis is actually, I look at each of the training image and then fix their label in certain order. If you do random order, right? So the accuracy is going to improve slower, right? But if you kind of order data example using the Shapley value, right? As you can see, you can actually improve the accuracy kind of much faster. And then you can actually try to debug it when you realize your system is not robust. For example, you could have a training set with a lot of backdoor examples, right? So, and if I have a test set with some backdoor pattern, you say, I mean, on this example, right? So my accuracy is pretty low. You can also use Shapley value to actually debug it, right? You can actually look at those examples with negative Shapley value, right? And also try to calculate the Shapley value and try to identify those examples. And if you see, they have a wrong label, then let's flip it, right? So as you can see, compared with the random way of debugging this, right? By following the Shapley value, you can actually do this in a much more efficient way, right? Fan did an amazing job, right, to figure this out, right? So, okay, so I think I'm running out of time, right? So you can also use the data cleansing, but let me skip this part, right? Like essentially there are two views about input perturbation, right? It could caused by some adversarial parties where you have the robustness result. But on the other hand, it could be injected by the nature and they are maybe just pure noise, right? So in that case, you can actually try to calculate which input cell the noise is most important to the final utility, and then you try to clean them, right? So the way to clean it, kind of try to minimize the entropy, right? I'm not going to detail here. Yeah, so that's all I have today. I think I'm just on time. Yeah, so like again, right? So this is something we have been doing over the years. We start from a database perspective, then work together with Bo and also many other collaborators, right? To try to understand, like get something unexpected to us. It's at least in the beginning, right? So it's be done without all the amazing collaborators we have. And also, again, the real hero is always our amazing students, right? So if you're curious about this project, right? So they're actually part of a project called Datascope. And also they are also part of an even larger project called ESML. We also have to work about distributed machine learning. If you're curious about them, check them out. Okay, great. Again, thank you so much for inviting me. And I'm happy to answer whatever question you may have.
Yeah, thanks for your great talk. So we have a question in the chat. So a boy is asking, do you think it's possible to connect the entropy analysis for data uncertainty with Shapley? So that is with more noisy data be of low Shapley value. If they are more independent, should I clean data of high Shapley with higher priority if they have similar level of uncertainty?
Yeah, so that's a very good question. Yeah, the short answer is it's definitely possible, right? So I think there are a principal way to combine these two. I think mathematics is possible. I'm not sure under which condition is still in P time, so that I'm not sure. That we need to think about it. But definitely very, very interesting, right? So when we do Shapley, we actually don't consider data noise. We don't kind of understand uncertainty. Whenever we do uncertainty, we don't care about essentially the importance of existence of each data example, right? So combining these two is definitely very interesting. I would bet my money on if that we can still get a p-time algorithm for that, but don't hold my word on it. Yeah, so that's a very good question. Like I have no idea how to do it, but I believe it's possible and going to be very useful if you're able to do it, right? Yeah.
Yeah, just to add on, I'm thinking whether it is possible to make the algorithm actually more efficient rather than less, because here, if you need to compute all the uncertainties for all the existing data, maybe that's expensive. But for example, with Shapley, it will provide you a hierarchy structure to select the data that you want to focus on, right? Is that possible? So that it actually will be a first layer of data selection for you, I think.
Yeah. So I think that's a very good point, right? So you could, I mean, it depends on what view you take, right? So you could take the view like, okay, Sharpie value will give you a prior on each data example, right? So in that case, you make a search space actually larger, right? So, but you can also take a view similar to the mixture of expert, right? So you say, okay, out of this example, I only care about top K, right? In that case, of course, it's going to be simpler, right? Depending on which view you take, but I think you are right. Potentially, it could give something that even more efficient than just doing one on itself. Yeah.
Okay. Yeah. Thank you.
Thank you.
Yeah, so I guess another question is that for the backdoor, you kind of show some theoretical proofs for some KNN classifiers. So have you tried empirically for applying these backdoor defenses to more complicated deep neural networks? So it doesn't need to satisfy some theories, but have you tried empirically?
Oh yeah. So we tried it empirically. Actually, both tried it empirically. Yeah. So as you can see, I have no idea about this. Yeah. So yeah. So she has one amazing student, right? So and they actually tried out. We have one archival paper like up there. So essentially, you can do that for generic classifier, right? So you can actually sample a whole bunch of training set, and then you train for each one of them. You aggregate, right? So that actually works. So the problem there is that it's going to be very slow, right? So if you do k-nearest neighbor, you have a p-time algorithm going to be fast. But empirically, if you look at the robust accuracy, I mean, yeah, both works. Yeah.
Yeah, I think I want to add the certification for neural network also works. It's certification, not only empirical, right? But it's just not p-time runtime in terms of computation complexity. But the certification itself still holds for neural networks, just like randomized smoothing, right?
Yeah, that sounds great. So another question is that for the so you have shown that that you can get some theoretical results for backdoor poisoning. So have you considered the poisoning other kinds of poison attacks with different attack purposes or different threat models?
Yeah, so that's a good question. So we haven't, right? So but I think there are other papers try to do something in that direction, right? So for example, paper I think from Zico about how to do label flipping attack, right? So how to have a certificate for that. So I think people are moving toward that direction to understand what type of thing you can certify for poison attack, right? So I think we are doing our threat model and definitely interesting to turn to other things, right? And people are doing that, yeah.
So Bo, do you want to add on that?
Oh, I think also with so we have maybe too many collaborations. So we also have one certification against the semantic type of perturbations, not only LP bounding. So that could be considered as another threat model in addition to LP evasion, in addition to backdoor. That's an evasion based on semantic attacks. Yeah, people can interested can check out. It's a CCS this year.
Okay, sounds great. So thanks a lot, for your great talk.